I'm thinking this will be a series of videos. There's a lot of information to go through, and I'll try and make it short and sweet. So we're gonna talk about forces, and let's start with what the heck a force is. A force, easiest definition, is just a push or a pull. We don't typically care if it's a push or pull. It's all relative, but that's the definition: push or pull. There are four natural forces, and those are the strong force, the electromagnetic force, the weak force, and gravity. The strong force is responsible for holding together the nucleus and kind of actually like binding the particles that make up the subatomic particles together. It's going to be our strongest force. The electromagnetic force, it's going to be our explanation for a lot of our what we call contact forces. So like if you are pushing a box, well, we don't really, I'm hesitant to say this, but we're not really interacting with the surface of the box. The particles, the charged particles that make up our hands, our fingertips, our palms, the surface of the box, those charges have attractive and repulsive forces, and so that can actually explain our contact forces. We are not physically we are not touching the box necessarily. It could be that the particles are interacting at a distance to push each other apart. Like particles or like charges repel, whereas opposites attract. And so the outer charges on our skin and the outer charges in the door, and since those are kind of a little more free to roam, those could repel, and that can actually explain contact forces, and we'll get to those in a bit. The weak force is responsible for radioactive decay, and then there's gravity, which is weird because it is actually the weakest force. So I don't know where they got the name for weak force, but here we are. So out of these four fundamental forces, the strong force, let's say, relative to the other three, it has a strength of 1. I don't care what units. The electromagnetic force, so this is the strength of 1. The electromagnetic force has a strength of 1,000th of the strong force. And obviously this is not to scale. We can take that a bit further, and the weak force is going to be not 1/16th, but have a relative strength of 10 to the 16th compared to the strong force. And gravity, it's sitting at a relative strength of 10 to the negative 40th. And hopefully this makes a little sense. We really only see the effects of gravity when very massive objects are involved. We don't notice the gravity between each other. We only notice the gravity, the gravitational force between us and the Earth. So we don't see pens accelerating towards the wall unless we push it, right? So gravity is going to be our weakest force, and by quite a lot. The thing is, they act on different ranges. Both the strong force and the weak force really only are effective at short ranges relative to the electromagnetic and the gravitational. Those have a range that is infinite. Now, because forces can pull in all directions, like gravity will pull people down, but if we're on the other hemisphere, it would also pull people down, but they have a different down relative to them. So these pushes and pulls, like we could push on the box or pull on the box, they all have direction. So all these forces are vectors. And I didn't mention units earlier, but if we talked about units, we use what is called the Newton. In everyday parlance, we're typically using pounds for force, but for physics we use newtons, and 1 Newton is enough force to accelerate 1 kilogram of mass at 1 meter per second every second. Okay. So this would be like 1 Newton would be the weight of like half an iPhone. So 2 newtons would be, if you were accelerating that iPhone 1 meter per second every second, that would be about 2 newtons of force applied. So these are our 4 fundamental forces, and they're going to make up the rest of the forces that we talk about. And let's end right here.